Here, everybody has 3, 2, is that right? Okay. Go ahead and take a 3, 3 while you're at it. If you can take one too, because I don't have copies. Because we'll start into 3, 3. 3, 3 is a long section, but most of the content's pretty easy. Okay, so what we're going to be looking at in this section is just kind of looking at functions and finding information about given graphs. That's the main idea. So what you'll find in your homework, on 3.2 is probably something you'll be able to do fairly quickly. A lot of what you're going to have is you're going to be given a graph, and you're just going to answer questions about it. Some of this stuff we've already talked about. Okay, so that's the graph I gave you. So the first question I have to you on that, based on what we've learned, is that a function or not?
No.
Yes or no? No. What did we learn? What's the way that you can tell if something's not a function? Yeah, the vertical line test, okay, like that, okay? So the idea is, yeah, if you took a vertical line there, what that means is you found an x that has 2 y's, and you can't have that. Every x has to have 1 y in a function, so that is not a function, and that's basically by that vertical line test. Okay, so that's the idea there. You want to be able to quickly tell if something's a function or not by its graph. Okay, let's look at the domain. Now, if I want you to give me the domain, what are you looking for? You're looking at what x can be, right? So notice on this, there's a graph here. Okay, so basically you're going from negative infinity until you get to that negative 3. There's no graph there, so that's not part of the domain. And then from here you would have 3 to infinity like that, okay? Now generally, and the way this is, like if it's not a function, you don't necessarily go through and do that, but I want to go through and do that and do the intercepts and everything. So the domain, if you wrote that out, you would be going, this is a relation. It's not a function, but it is what we call a relation. So the domain, you would say negative infinity to negative 3, and you would include negative 3, because that's a definitive point on that graph. Then you would go union, then you would go 3 to infinity like that. Okay, so that's what x can be. Okay, the range, what do you look at? You look at what y can be. So how about y? Anything? It's getting higher and higher and higher, right? And it's getting lower and lower and lower. So, I mean, if you trace this thing out, it's just, there's no gaps in the y. It's going on forever. So what you would have for your range, if you did interval notation, you'd write that like that. Okay? Now, the way this will go on my math lab, I know, is if it's not a function, you're done with the problem. They won't even ask you the domain and range. But it is what we call a relation, so you can have a domain and range of a relation. Okay? All right, what are the x-intercepts? How many x-intercepts does this have?
2.
It has 2, so one of them's 3. And I always want you to write these as not just numbers, but as points. So 3, 0, that's an ordered pair. You want to write that. The other one is negative 3, 0, like that. Write them that way. I want you to do that. What are the y-intercepts? There aren't any, okay? Never happens, okay? Now, this stuff, a lot of this we've talked about. How is that symmetrical? X-axis. I see that. Anything else? Y-axis. Okay, anything else? Origin's the one that's tricky for students. But, you know, what happens on this is if you take a couple of points on here, it's pretty clear that this one is symmetrical about the x and y-axis by looking. So I want to take like a point on here. What you might want to just write this on here. See, like you have a point 3, 1. Is that 3? No, that's 4, 1. So let's change that. So you can always, if you're in doubt, you can just kind of look at some points. So notice you have 4, 1. And then over here, and I'm approximating that, that's negative 4, 1. Now that's what makes it symmetrical about the y-axis, is when you have opposite x's, you have the same y. So without a doubt, that's symmetric about y. But notice you also, looks like you might have a point 4, negative 1. And over here it looks like you have a point negative 4, negative 1. That's what makes it symmetric about the x-axis, is when you have the same x, you have opposite y's. And that happens everywhere on that graph, right? Okay, now that's the way that goes. Now, if you want to look at origin symmetry, here's what you do. If you have 4, 1, then you would expect negative 4, negative 1 to be on there, right? Origin symmetry is if you have a point, then if both things are opposite, it's on there. Look at this one, 4, negative 1. What's the opposite of that? Negative 4, 1. So that looks like it's matching up to me. And what happens on origin symmetry is like this. So if you do origin symmetry, if you fold over x, they come together. Or sorry, if you fold over y, they come together. But then if you folded over y, they would come together. So you would be symmetrical about the origin also. You guys understand what I'm talking about by that? If you fold that over, they match. And then you would have that. Now if you fold it over, they match. Okay, so that's symmetrical about the origin. That's the one that's a little bit harder to see. Now, if you have trouble seeing that, just get some points and see if that satisfies those conditions we expect. Okay, is everybody with me there? Okay, so it can be symmetrical about all three of those. Okay, let's look at, just some more. This is a lot of what you're going to do is given graph, answer questions about it. Okay, problem number 2. Would you consider that a function? No. How come? Vertical line test fails, and you got a circle on that, so a circle's not a function. Okay, now we're going to go ahead and do domain and range. What's the domain in interval notation? -3 to 3, okay? These are going from there to there, so it looks like your domain is -3 to 3. What's the range? What are the y values ranging from? -3 to 3 again. Yeah, okay. So it goes like that. Okay? All right? All right. How many x-intercepts does it have? 2. How many y-intercepts does it have? 2. So remember, we write those as points. So your x-intercepts, it looked like, would just be -3, 0, and 3, 0. And then your y-intercepts would be 0, 3, and then 0, -3 like that. Okay, so that's how that goes. All right? Everybody with me there? Okay? All right, now the hardest thing is the origin symmetry. How is this one symmetric, just in your head? Is it symmetric about x? Yeah, how about y? How about the origin? Yeah, see, try to think of the origin this way. If you fold it across the x-axis, this arc would match that, right? Now, if you would end up with that after you folded your paper. Now what would happen if you folded this way? Would they match? That's it. So origin you can think of folding over x and y in either order. Okay, and if they match perfectly, then it's symmetrical about the origin. Okay, and those kind of things, you're just trying to kind of quickly look at that in your head. Okay, all right. Okay, let's look at this number 3 here. Okay, number 3, is that a function? Yep. Okay, that passes the vertical line test. Now the domain, this graph's kind of weird. What it's supposed to be doing is this thing is supposed to be getting close to the y-axis but never touching it. Okay, and a lot of you probably have a background, you've probably maybe learned about asymptotes before. But what's supposed to be happening on this problem is it never touches the y-axis, it just gets close to it. Okay, so and this is supposed to go on forever. So if you wrote the domain, it would be going from 0 to forever, right? But you would exclude the 0. Okay, and that's one you just have to assume that. I mean, you can tell that I drew that so it just sort of approaches the y-axis but never hits it. Okay, now how about the range? What would that be? You're going this way now. Y is getting infinitely high, so it's going to infinity. How about infinitely low? It is, okay. This thing's never leveling off. You just kind of assume it just keeps going down like that. Okay, so your range would be all real numbers, okay, like that. There's no gaps in the range, okay, but the domain is 0 and then forever, but the range is like that. Okay, let's see, x-intercepts, what's the x-intercept? Looks like you got 1. 1, 0. How about the y-intercepts? None. Yeah, I said that you kind of got an asymptote on that one then, so that one goes like that, okay. All right, let's look at the symmetry. So if you folded over the x-axis, would they match? No. Okay. Yeah, if you folded, this thing would go down there. So it wouldn't match the rest of the graph. So that's a no. Okay, how about y? No. Okay, same thing would happen. If you folded this over the y-axis, there's nothing even over there to match with. So it's definitely not symmetrical about y. How about the origin? Nope, not that either. Okay, because again, what happens on the origin is basically this. Like this is a point, and I don't know if that's a point like 4, -2. If it's symmetrical about the origin, there would have to be a point -4, 2, and there isn't. Okay? So that can't be symmetrical about anything then. All right? Okay? Any questions? Okay, I think this stuff usually goes pretty smooth for students. Okay, now this one is this is really a trigonometry graph, but you know it doesn't matter if you don't know anything about trigonometry. It's still basically the same thing. All right, so the domain on this would be it's starting here and it's ending there, and there's no holes or anything. It's a nice smooth continuous graph. So the domain we would say from negative pi to positive pi like that. Okay, how about the range? Negative 1 to 1. Yeah, okay. The lowest y is negative 1. The highest value of y is positive 1. Now, you do include those in brackets because they are included points on there. Well, you got a bunch of x-intercepts, okay? So I'm just going to kind of list them out, so that's what we got to do. Now, I'm not going to do points, okay? I'm just going to do like this. For the x-intercepts, let's just say what x is. So that would be like negative pi. That's probably negative 3 pi over 4 is what that should be. Okay, then you would have negative pi over 2, negative pi over 4, 0, and then we would have pi over 4. You could even use plus or minuses. Pi over 4, pi over 2, 3 pi over 4, and pi like that. Okay, you're just listing all of the x-intercepts on that. When you get to, if you take trigonometry, you would find that this graph probably, if it went on forever infinitely, you would have to write a formula for the domain. So you kind of learned that in the trigonometry class. Okay. The y-intercepts, it does have one, so that one would just be the point 0, 0, so you do have a y-intercept. Okay, this one, let's look at the symmetry. The symmetry on this one, let's start by looking at x-axis symmetry. So imagine folding over the x-axis. Look at this point here. Would it match anything? No. No, so you can forget x. Okay, how about y-axis symmetry? If you folded it over the y-axis, this little point right here would have to be there. Is there anything? No, there isn't. Okay, so it's not that. Now let's look at origin, and let's kind of look at that a little bit and see on that one. That's one sometimes a little harder to check out. So what you would have on this, I can just give you one example on this. So like this point right here, I don't know what that point is, but that might be around, it's some number and it's 1. So you would have to have the opposite of that and negative 1. Now this one's kind of tricky right here. So basically if you reflected this over the y-axis, that point would be there, right? But then if you folded it over that, it would match, wouldn't it? Okay, and let's just think about whether that always works. Take this point right here. If you folded it, that would go to there, okay, like that, I think, because that's pi. You'd have, like that point there would kind of be there. This thing's starting to mess up. So if you folded it down, it would match. That is symmetric about the origin. That's a little hard to see, but, okay, if you actually fold it over both axes, they do match, okay? Is everybody with me there? That's a little tricky on that one, but that does look to me like it's symmetrical about the origin, okay? All right, so that's the first kind of thing that you want to make sure that you know how to do. You're given a graph, and what you want to do on that is be able to answer questions about it. Okay, that's typical just observation of graphs. Okay, next thing we're going to look at, because typically in this section we're just kind of learning basic properties of functions, is some things like this. I'm going to just kind of go over this. Let's say that you have a function, and we're not going to graph this or anything. That's the function. We want to know if that point's on the graph. How do you do that? What? Plug it in. Plug it in, exactly, yeah, okay. Because that's an x value right there, and then that's the function value. That's really y like this. So what you would do is f of x is negative 9 when x is negative 1. So you'd have 5 times negative 1 squared plus 10 times negative 1 minus 4. Remember what a graph is. A graph is a solution. It's a picture of all the solutions of that function, of that equation. So if it works, it's on the graph. So that's going to be negative 9. This part right here looks like that would be 5. That part there would be minus 10 and minus 4. So if I'm doing that right, that looks like you have a negative 9. And on the other side, is that negative 9? Yeah, okay, that is negative 9.
Wouldn't that first one be 25?
No. Okay. I kind of did that in my head too. This one right here.
Yeah.
Because you're squaring a 1, which is a 1.
Oh, okay.
1 times 5 is 5. Okay, I understand. You're thinking,
Yeah, no,
maybe you were
yeah,
seeing it as
no,
5
twice.
squared.
Yeah.
Okay, so that one looks like that would be a solution of that equation if you plug that in. Okay? All right, go ahead and do the next one. Just go ahead and don't wait for me. Go ahead and just see if that's a solution or not. Just plug it in and see if it works. So that first one is definitely going to be a solution. They either work or they don't. Is that working? Doesn't look like it's working. Okay, so if you did your arithmetic, I went ahead and did the arithmetic up here. You should, if you did the arithmetic right, you get 1 is equal to 7. So that would mean that no, that's not a solution. Okay, because those two numbers are not equal. Okay, that's just a arithmetic problem. Plug in the 1 for the function value and plug in -2 for the x. That's how you tell if something is a point on the function or not. Okay, all right. Okay, next thing we want to look on this is it says you're given this function and we want to look at the y-intercepts, okay, if there is one, okay. Well, first of all, what you always want to do if you're doing a y-intercept is always going to look like this. It's always going to be 0, comma something, right? Because if you're on the y-axis, x is 0 and you're just up or down. So the way that you find a y-intercept is you just set, everywhere you see an x, you set that equal to 0, and you work it out. So in other words, what you're doing is the function value f of 0 when you do a y-intercept. So that would just give 0 squared plus 4 over 0 minus 9. Okay, if you work out that arithmetic, that's going to give a 4 in the numerator and a -9 in the denominator. So that means the y-intercept is 0, comma, and I'll just write that as -4/9 like that. That's how you always find y-intercepts. Now, there are times when you might not have a y-intercept. I mean, there's lots of functions that don't have a y-intercept, but that would be where it crosses the y-axis, okay? That's how you always compute that, okay? All right, everybody with me and everything okay? Okay. How do you find an x-intercept, by the way? You set y equal to 0. Then you have to solve an equation. Sometimes it's a little bit harder work to find an x-intercept, but you always set the opposite variable equal to 0 and then solve, okay? All right? So just a couple more pages on this. We don't do a whole lot in this section. It's a real short section. So on this next one, I always like these problems. These problems kind of make me laugh in some kind of way. This is basically a problem to see if you can take a scenario. Yeah.
I don't have this page.
You don't have that page?
I don't have that page.
Really? I guess the copy machine ate it. That's okay. I'm still going to go over the problems, but you don't have to write them down. Okay? This is just something that's kind of good to go over in class, okay? I always like these problems. So what this is giving you, and you'll see maybe a few of these things on the homework. So what it's saying is, which of these graphs would basically tell what this problem's saying? It's saying that you have the amount of rainfall as a function of time if the rain fell more softly. Okay, well, let's look at what each of these graphs mean. Okay, this graph right here, this is time, and that's amount of rainfall. Right now, at that point in time, there's no rain, right? What's happening? It's raining, okay? And it's raining pretty hard because the value's getting bigger and bigger. What's happening right there? It stopped. Now what's happening? It's raining, but it's not raining as hard as it did there, right? Does that make sense? Okay. Now look at this one. Okay. Well, right now it's not raining at all, but it's raining pretty hard, but what's happening to the rain? It's leveling off. So that one is falling more softly. What's this one doing? It's raining and it's getting out of control. The whole world's going to flood. Okay, that's what that means. And then this one means that rains for a while, that quits raining, and then it starts raining real hard forever. Okay, so that's the right one right there. Okay, does that make sense? Okay, I always like these problems because some of the graphs are kind of funny. Okay, let's see. Do this. And again, you don't have to write these down. This one's just the height of an animal as a function of time. Well, let's see what this is. So let's go to D. Okay, right now at the beginning of time, the animal is 0 tall. Then they get taller and taller and taller, and then they do that, and then what happens to them? They shrink, okay? So forget that one. How about this one, okay? What happens to the animal? They get taller forever, okay? How about this one? They're born tall, and they shrink for the rest of their life. How about that one? Is that more logical? Yeah, you grow and then you level up. Actually, technically, you do shrink as you age. Your bones actually lose a little bit of mass. I'm probably at the age where I'm starting to shrink a little bit. You guys are probably too young for that. But actually, that's supposed to be what happens, okay? All right, so that one would be that one. I always like those props because they're kind of funny if you look at the graphs and think about them. Okay, now you guys do have the last page, is that right? Okay, so we'll just do this last problem here. And this is actually an interesting problem. This is something that's actually real. Is it turns out because of the way gravity works and everything. So this is basically what this is saying is you have an object that weighs m pounds at sea level, and then the weight is going to be given as a height. This is a function right here. And what this is in this function, okay, that's the mass. Right there, that's the number of pounds. Actually, mass is more like in grams and stuff. But what's happening on this is that's the height. So what happens is, gravity is a little bit different at different elevations. So if you climb up, what's the tallest mountain in Colorado? Mount, can't remember, Algebra, okay, around Leadville. So if you go all the way to the top of that, actually you lose a little bit of weight. Not much, you wouldn't notice anything, but you lose a little bit. Okay, and then of course if you keep going up until you get into space, well then you weigh nothing, because there's no gravity. So what's happening on this is we're going to take like this thing right here. We have, you're starting off at 165 pounds, and then we're going to go all the way up to, a tall mountain, 14,490 feet above sea level, and then we're going to see, well, how much did this person lose weight, okay? Right, so this goes like this. So what we're doing is we're doing W of 165. This is a calculator problem too. So what we'll do is just plug this in. So we'll have 165 like that. And then let's see. Then what we'll have is we'll have the 4,000 here. And then all over 4,000. And let's see. We want, we're going to plug in the height. So the height on that would be 14,494 feet. Then we square that like that. Okay, and I think the units work out on this. I don't think I'm missing anything with the units. Let's just try and see what happens on this. Theoretically, what's supposed to happen is the answer should be just a tad bit less than 165. Now I'm going to put this in my calculator and just kind of put this in one step. So I have the 165 parentheses 4,000. Okay, then divide by, now if you do this in one step, you'd have to have that denominator in its own set of parentheses. Okay, so that would have to go like that. Double up on the parentheses and square it. So if I got my calculator right, let's see what this is. I did something wrong. There's no way in the world that person could weigh 7 pounds. I was wondering on this if that might need to be in miles. Okay. All right. That's when I was doing this, I wasn't sure if the units were going to work out or not, but I suspect it has to be in miles. Okay, if I remember right. Let's do this real quick because now I'm curious. That's obviously a ridiculous answer. So if you have 14,494 feet and we change that to miles, it'd go like this. Okay, there's 5,280 feet in a mile. I'm just curious if that would be what I may not have wrote down what the units are supposed to be on this problem. Okay, so basically if I do 14,494 and then divide that by 5,280, okay, that would be, around 3 miles. So that's about like that. So let's try this, okay? Instead of doing this, let's take that out and let's try miles. I'll just say 2.74 there, and let's see if we get a better answer, okay? And I think that's what the deal is your units have to be a certain way. So I'll try that again, okay? I'm going to do 165, and then in the parentheses, I'll have 4,000. Then I'll divide by a new set parentheses. I'll have 4,000, and you can do that in your head, plus 2.74. Then you'd have to double up on the parentheses. I'll make sure I've got that okay, so that looks good. Okay, then I got to square it. Okay, let me see if this is any better. There we go. Okay, that's what I thought. Okay, so this person didn't lose too much weight. They're about 164.7. Okay, so that is true. Okay, I mean, you do actually, weight is relative. Okay, and if you're on the moon, you weigh a lot less because gravity is a lot less. Okay, that's the idea. Okay, if you're on a surface of a planet with really high gravity, then you're going to weigh a lot more. That's the idea. Okay, I just thought that was kind of interesting, but that did have to be in miles. Okay, all right, so that's it. That's all you do in that section.